And then I'm just gonna introduce you and go through your bio. That's
okay.
On there, and then I'll just pass it along to you.
Sounds great. So Rashmi, I'm going to go offline for just 60 seconds. I'll be right back.
Sounds good.
So good morning, everybody, or good afternoon. We're still, I think, waiting for people to congregate, and hopefully we'll get started around noon or so.
David, I've also made you co-host. That gives you some more functionality, I think.
Excellent, thank you.
Well, it looks like it's top of the hour. Should we give it one more minute and then we can start?
Sure, that sounds good to me.
Meanwhile, everyone who's coming in, welcome. Right. I think I'm going to go ahead and start. I see some more people are calling in. Everybody who's called in, welcome to today's talk. Today's talk is organized by the Metro Los Angeles GRSS chapter. And the topic of today's talk is NASA's EMIT Imaging Spectroscopy mission, and it's going to be given by Dr. David Thompson, who is a principal research technologist at JPL. Before I go into his bio, I would like to introduce myself. I'm Rashmi Shah. I'm the chapter chair of the MLA GRSS chapter. And if you would like to be involved or are interested in talks like this, would like to give one, please feel free to reach out to the MLA chapter. And you can find that information on GRSS website on how to reach us. But it's la.grss.officers@ieee.org. That's the way to reach out to us. All right. With that, let me introduce today's speaker. Dr. David Thompson is a research principal technologist at JPL, which is a part of CalTech and NASA. He's a technical group lead of the JPL Imaging Spectroscopy Group, instrument scientist for the NASA EMIT mission, and investigation scientist for the NASA Airborne Visible-Infrared Imaging Spectrometer project, or AVIRIS project. His research uses spectroscopic data to characterize Earth and other planetary bodies, with additional emphasis on real-time applications. His algorithms have guided autonomous robots and sensors fielded in North America, South America, the Atlantic Ocean, airborne campaigns, low Earth orbit, and surface of Mars. He's the recipient of NASA Early Career Achievement Medal, the Lou Allen Award for Excellence, and the NASA Software of the Year Award. With that, I'll hand over to David.
All right, well, thank you so much, Rashmi, and thank you to everybody for coming. It's a pleasure to share this information with you and to tell you a little bit about what we've been working on for these past 6 months or a year, and what we can look forward to as far as the EMIT mission in the years to come. So big thanks to the LA chapter for organizing this, and to Rashmi in particular for setting this up. This is a great pleasure. My objective for this talk is to introduce you more broadly to imaging spectroscopy and the measurement technique, to give you some context for why we think EMIT is an important mission and how it's sort of a harbinger for things to come. In particular, the surface biology and geology investigation that NASA is planning right now for the coming decade, and how this really has the potential to revolutionize Earth science remote sensing. And so those of you who aren't familiar with the imaging spectroscopy methodology, I'll be providing some examples to show you what it's about and kind of how the data analysis works. But EMIT, of course, is a particular example of that. And so we'll also be spending some time on the EMIT mission itself to give you some background about what it is we aim to accomplish. It's a fairly directed mission, so it's not a general purpose land imaging mission. We have a very specific science focus. And so I think you'll find it interesting. And then finally, I'll talk about some of the more specific analysis techniques that we're using, and in particular, some of the validation strategies that are kind of unique to this mission, how we'll be validating our various analysis algorithms in the field using spectroscopic techniques. Okay, so without further ado, let's get started. It goes without saying that I'm just one member of a much larger team, and I'm speaking in particular on behalf of Robert Green, who's the PI for this mission, and Natalie Mahwald, who's the deputy PI from Cornell. And a much larger science team as well. I thankfully get to be their spokesperson today, but I am just that. And there are a lot of people behind the scenes and in the forefront making this work. So this first picture on the front page here. Oh, and I should say also, I don't know y'all's background as far as exposure to these methods before. So if I say anything that's obscure, please go ahead and shout it out as I'm speaking. We can kind of keep this informal and field questions as I proceed. And that way I'll make sure that I don't miss any key context for your understanding. So let's get started with this first image on the front slide, which sort of encapsulates what the EMIT mission is about. You'll see here off the coast of North Africa, off of the coast of Libya, a couple of dust plumes being lofted into the atmosphere. This image was captured by MODIS, but it's one of many, and it represents part of the dust cycle of planet Earth, where dust is emitted from dry lake beds and playas and other surfaces and cast up into the atmosphere, where it exerts a radiative forcing effect. And you can see that the dust from these two different sources surfaces has a really distinctive color, right? Whether it's sort of this ruddy color off of this coastal surface or from the inland, this bright color. And actually the dust composition and its spectral absorbing properties, that is, broadly speaking, its color, has a big impact on its radiative forcing and its effect on the climate system. And so that's part of what the EMIT mission aims to measure. But kind of getting ahead of myself. So here's the agenda. I went through most of these already. Let's start from basics, right? From first principles. So there are a couple of sources of photons available to us for passive remote sensing of the Earth's surface, right? We've got the solar reflected regime, and I'm talking primarily about optical remote sensing here. Many of you, of course, are radar experts. That's a different ball of wax that I'll leave to other speakers. Here we're talking mainly about optical and infrared remote sensing. And there we've got two main sources of radiant energy. So we've got the sun's radiance, which is a hot black body, right at about many thousands of degrees Kelvin. And so it emits strongly in the blue end of the spectrum. And this is the red line that you see here plotted. So this is the solar reflected portion of the spectrum. And this is the portion that EMIT aims to capture. So everything from the UV out through about 2.5 microns, 2,500 nanometers is our playground. And indeed, this area is really useful for remote sensing for a couple of reasons. First, you can see in the background that there are some atmospheric windows. So I've overplotted the atmospheric transmittance. You can see that there are some plenty of windows here that we can use to probe down to the Earth's surface. And second, because this range is actually sensitive to a lot of very interesting physical and chemical properties of the Earth's surface. So we are sensitive to a wide range of different geophysical phenomena, which makes it a very interesting, excuse me, very interesting place to do remote sensing. In the longer wavelengths, we have another source of photons that I won't be getting to today, but many of the same techniques apply with slight modifications. This is the thermal infrared regime, the natural glow of objects at room temperature, right, in these longer wavelengths. So suffice to say, all of that exists too, but we're going to focus on the red curve here for today's talk. Imaging spectrometers are just that. They are imagers, but they're also spectrometers. So at every location on the surface of the Earth, we're collecting a spectrum, right? So instead of an RGB camera that would have 3 color channels, here we've got hundreds of channels representing the distribution of photons across the entire electromagnetic solar reflected wavelength regime. And EMIT, like many imaging spectrometers, operates as a push broom device. So that means it has a linear field of view on the ground. This linear field of view is enters a telescope at the aperture. It is cast onto a slit and then dispersed off of some dispersive element like a grating or a prism. In our case, it's a grating, but prism spectrometers exist too. And then the wavelengths are sort of sorted by, or the photons are sorted by wavelength and cast onto a detector array. So we've got a 2-dimensional detector array, just like in your phones. But of course, one of these dimensions is the spectral dimension. The other is the spatial dimension. So that gives us our linear field of view on the ground. And then in order to build up a map of the Earth's surface, we push that field of view along the surface as the platform orbits around the Earth, right? And that's what gives us our 3-dimensional data cube. So I'm going to stop here for a moment and just illustrate what this means in practice. So let me share a different application. This is an example of a application that typical of what we'd use to view imaging spectroscopy data. I hope you can all see this. This is software, open source software developed at CalTech that you all are free to explore if you're interested. But here I've got a scene, which is indeed the CalTech campus overflown by an airborne imaging spectrometer. So this is an airborne analog of what the EMIT mission will collect. And you'll notice up in the upper right corner of this application, we have a spectrum, which is the reflectance at the surface, right? So I'll talk a little bit more about what that exactly means, but you can think of this broadly speaking as just the fraction of incident illumination that's reflected back at the sensor, right? And if I click around this image, you'll notice that that spectrum plot changes to reflect the reflectance of these different surfaces. So if I click here on this lawn, you can see what is actually the reflectance of a lawn, which is a classic.
We're not seeing an image. At least a few people aren't.
Sorry. How about now? Does that help?
That's it. Yep.
Excellent. Thank you. Thank you. That was the test of the interactivity of the presentation. So please let me know if you experience any more technical challenges or any more goofs on my part. Here is the CalTech campus that I was referring to. And here is the reflectance spectrum up in the upper right corner. Can you see my cursor when I move it? Hopefully.
Yep.
Excellent, excellent. So this is the classic vegetation reflectance spectrum. You can see at about maybe 690, 700 nanometers. This is the red edge absorption of chlorophyll. You can see a couple of features here due to liquid water absorption in the tree canopy. There are other minor modulations of this shape due to, say, scattering properties within the canopy or pigments in the visible end. Regardless, suffice to say, this is vegetation, and it's because I've clicked here on this lawn. And as I click around, you can see that this reflectance curve changes as I move over areas with different composition, right? But if I were to click on something else, like say a white roof, right, that has a distinctive reflectance profile, and you can actually use these spectral shapes to infer things about the composition of the surface. So if I click on this green baseball field right here, you'll notice it's actually very distinctive from that vegetation spectrum, and that's because this is astroturf. It's not real vegetation, and the naked eye might not see that directly from the red, green, and blue channels, but you can see it. It's bloom and obvious in the spectrum. We have a hydrocarbon feature here at about 1700 nanometers, and then there's paint to make it look green, right, which is this green peak right here. So and there are other compositions that are apparent in the scene. A red tile roof has an interesting iron oxide hematite feature here. So you can really do physics and chemistry just based on the properties of this reflectance spectrum. And you can see that there's a huge diversity of different materials revealed in this simple urban scene. So that's generally speaking what we do when we do imaging spectroscopy. I'm going to switch back now. Unless there are questions about this, I'll just switch back briefly to the presentation. All right. Super. So anyway, that's how we collect these data cubes and what they're good for. I should emphasize that difference, the difference between reflectance and radiance, and this will come into play later in the talk. I was showing you reflectance spectra, that is the physical properties of the Earth's surface, but what we measure at the sensor is actually something a little bit different. We measure the radiance, that is the incident illumination in every wavelength, and this is influenced not just by the reflectance at the surface, but also by other factors like the distribution of photons coming from the sun, right, which is higher of higher magnitude and shorter wavelengths. It's influenced by absorption in the atmosphere. So these spiky features that you see right here at about 1 nanometer are water vapor absorption features from the atmosphere. And we have to account for all of that when we try and infer the reflectance spectrum. So this reflectance is really where the action happens. That's where a lot of the Earth's surface analyses take place. But a key part of the imaging spectroscopy technique is inferring this reflectance accurately from the radiance that we actually measure at the sensor. Okay, so what are some other applications, some earth science applications? Well, I'll walk through just a couple to give you a broad idea of the scope of different science themes that it touches on. So one common one is hydrology. So imaging spectrometers can be used to look at snow grain size of both snow and ice, to look at snow water equivalent, and studies of the condition of a snowpack to look at its hydrological implications. Also light absorbing particles on the surface that could affect its radiative balance, or the rate at which it melts. So these are all really important things to know if you're doing water resource management. And so that's a common application. Another one is to look at water quality and water productivity, both in the oceans and in inland waters. So here you see an example of these reflectance spectra that are changed as we increase the phytoplankton content in the water or increase the concentration of colored dissolved organic matter. It's sensitive to a lot of other kinds of water column constituents too, like just natural turbidity from suspended sediments. And there's quite a bit of work being conducted right now to actually infer the phytoplankton taxa, that is the taxonomic classifications of the different phytoplankton communities and their biodiversity based on subtle changes in this reflectance shape. So there's quite a bit of oceanography and ocean science that you can do. Of course, vegetation is another common application, both looking at terrestrial ecosystem productivity and health, but also diversity as well. And so here you see some examples of vegetation spectra, and also how these spectra change as we change the composition of each pixel, as we increase the fraction of woody plant tissues or non-photosynthetic vegetation versus the photosynthetic fraction. You can also do things like canopy chemistry, for instance, using different features of these canopy reflectances. But what we're mostly interested in for the EMIT mission, as you might imagine, is not the vegetation, nor the phytoplankton, nor the snow. It is rocks and stuff. So we're looking at mineralogy, and in particular, the mineralogy of Earth's dust-forming regions, right? And so most of the remainder of the presentation will be focused on the composition of Earth's surface in terms of minerals. And minerals, of course, have their own unique absorption signatures, and they actually act as fingerprints in the reflectance spectrum that you can use to recognize what the minerals are at any location. So here are some examples. So hematite and goethite are iron oxides, right? And they tend to have absorption signatures in the visible range. So you saw this before with the red tiled roof, but it's actually present over much of Earth's surface, actually. And this is one of the things we aim to measure with the EMIT mission. Here is an example of calcite and kaolinite spectra. So these are signatures in the shortwave infrared range that are also quite prominent and common at different locations. So let's, as just an example, let's look at the Salton Sea. It's pretty nearby for those of us living in LA. So this is actually an interesting dust-forming region. Here is a mosaic of images that we put together from an airborne instrument called AVIRIS that overflew this site many times, actually. But this is one of the acquisitions where it flew back and forth over the Salton Sea with its push broom imager, and we put all of those into a big data cube that covers the entire region. So this is an example of how we can build geologic maps using these data cubes. If you apply that spectral matching algorithm to every pixel in the scene, then you can get something that looks like this. This was produced by Roger Clark at USGS, who's one of the co-investigators with EMIT, and it shows all of the different minerals of the Salton Sea area that we were able to infer and map quite precisely and quantitatively without actually having to go down and touch them, right? We've got illite out here. We've got, I guess, various kinds of montmorillonite in the pinks and reds. I think there's an example of calcite. There's a calcite deposit right there. So there's quite a bit of mineral diversity even in this one scene. And the idea with EMIT is to take the same technique and apply it on global scales for the first time. All right, so I do want to emphasize before I go on and talk about the EMIT mission in particular, as long as we're talking about imaging spectroscopy, what's unique and different about this technique vis-a-vis the sort of multispectral imaging that's quite common already in Earth surface studies, right? So if you think about MODIS or Landsat or even high resolution planet data, these generally operate in a different way. They've got a camera or a push broom with different filters, right? And that gives you a couple of discrete channels maybe across the spectral range, represented here by these lines, right? The spectral response spanning each of these spectral ranges. So this gives you some idea of the magnitude for each of these discrete channels, maybe 1 to 10 bands, maybe a couple of dozen at most. They tend towards more image-based or morphological analyses or potentially empirical models that are constructed with band ratios and other things. They're often mathematically underdetermined, meaning there are confounders that can't necessarily be separated using the data itself. You'd have to go to external sources to recognize, say, aerosol contamination of a vegetation measurement. And that tends towards more qualitative or empirical rather than quantitative physics-based modeling approaches. Spectroscopy, on the other hand, is numerically overdetermined. So these are commonly constructed with prisms or gratings. They have hundreds of bands across the region, so we can distinguish all of the unique minerals in this one pixel. So here we have dolomite, kaolinite, and hematite all present in the same pixel, and we can quantitatively measure the aerial coverage of each of those minerals by analyzing their absorption features and actually fit that to physical models of the processes underway within that pixel. This is something that you can't do with a numerically underdetermined system. So it's a very different kind of measurement and one that tends towards more quantitative analysis with rigorous uncertainty propagation and measurement of uncertainties. Imaging spectroscopy, we're sitting on kind of the cusp right now of some dramatic increases in the quantity and quality of imaging spectroscopy data. So here on the horizontal axis, you see the year. And so we're sitting here in 2020. The vertical axis represents, you can think of this broadly speaking as science utility, right? Moving from targeted observations by visible to near infrared instruments to visible shortwave infrared instruments to global coverage of the same. And you can see that a wide range of agencies, different international space agencies are underway, producing and flying imaging spectrometers of various kinds. There's HISUI from Japan, NMAP will launch shortly from DRL. Here's the EMIT mission. We're targeting sometime in 2022, so maybe a year or 18 months before we start getting EMIT data, and that will last for a nominal mission of about a year. But then we've got other missions that will have even denser global coverage. So the CHIME mission proposed by ESA and the SBG investigation proposed by the Earth Science Decadal Survey for NASA, and targeting maybe, 2027 or 28 timeframe, sometime around that period, will provide global coverage on a bi-weekly repeat, very similar to Landsat imagery, but instead of just a few bands, you'd have the full spectrum from the visible through the shortwave infrared. So this will really be a revolution in the quantity of data that's available, and EMIT is sort of a pathfinder in some ways for the techniques, the analysis that we'll be using to look at those data sets. So the SBG investigation has a wide range of different science objectives, as you might imagine, everything from, and here, this is just a laundry list, so don't bother about reading all of the details, but there are actually many of the themes that we've already talked about, things like aquatic and terrestrial ecosystems, snow and ice. There are a wide range of geologic objectives as well. And so this is, again, a huge diversity of different science themes that will be that will benefit from the surface biology and geology mission. And EMIT gives us a chance to prove out many of these techniques ahead of time. Okay, so before I go on to talk about the EMIT mission specifically, do we have any questions on the imaging spectroscopy measurement method? Great. Well, in that case, I'll go on. So there's a dust cycle, just like there's a carbon cycle or a water cycle or an energy cycle, right? But there relatively little is known about where dust comes from and where it goes. These events tend to be transient, so you get dust plumes that happen in sort of a transient fashion from one year to the next or seasonally. But it's difficult to quantify the extent and the impact of dust simply by trying to image those dust plumes, right? They're temporally variable. And moreover, it's difficult to tell from optical instruments exactly what the dust plume is doing. A far better way to understand the impact of mineral dust and to predict its influence in the future as our climate changes is to understand the full process. So EMIT is a mission not just to image dust, but we're rather trying to understand the dust cycle with the help of models. And so in fact, we're not going to be looking at dust in the atmosphere at all. We'll be looking at the areas that produce mineral dust, that is the dry lake beds, the open playas, and other areas that produce mineral dust, to try and understand their composition. It's really the composition of the mineral dust that governs its impact, its ultimate impact on radiative forcing. And that's really the big uncertainty in Earth system models right now that are trying to model dust impact. So we'll be looking both at dust forming regions, and we'll also be looking at areas adjacent to dust forming regions. So these are areas that may be under cultivation, they may be slightly vegetated, they may be on the interface of desert or arid regions that are maybe vulnerable to desertification in the future. So the idea is if under future climate scenarios, those areas were to become desert or become dust forming, we would better understand what the resulting feedback and impact of those additional dust forming regions would be on the climate system, because we know their composition as well. So it really is a geologic mapping mission, ultimately. The dust is generally eroded off of these surfaces. It's entrained into the atmosphere. It will deposit out of the atmosphere either through dry deposition processes or raining, but in between, it does exert a pretty significant radiative forcing impact. And in fact, although the impact is not as large as some of the big, say, greenhouse gas players like CO2 or methane, the uncertainty in the dust radiative forcing effect is of the same order of magnitude. So it's really important that we improve our understanding of mineral dust in the atmosphere in order to make confident predictions about how the Earth's climate will change in the future. So the EMIT science objectives are to constrain the sign and magnitude of dust-related radiative forcing, both at regional and at global scales. And we do this by acquiring, validating, and updating the surface mineralogy that's used in Earth system models. And then, as I mentioned before, we will predict the increase or decrease of available dust and dust sources under future climate scenarios. And so we'll be running different climate scenarios into the future to see how these new regions, these new dust-forming regions may or may not affect the climate. We have a huge science team, well, a relatively large science team. This was a NASA Earth Venture Instrument Program mission that was selected. So it's a PI-led mission led by Rob Green at JPL with Natalie Mahowald as the deputy PI. I'm the instrument scientist for the mission. We also have a bunch of CLOIs ranging from geologists, field geologists, to remote sensing theorists, to atmospheric scientists, to folks looking at Earth system models, and really, you name it, there's a member of the team with that specialty. So it's a really talented group, and I'm really thankful to be a part of it. So the EMIT instrument itself, so for those of you who aren't familiar with optical design, it's relatively rare in its simplicity, right? We have that you could just probably count the number of optical elements on one hand, right? We've got the a Dyson block, which is a big lens. We've got a grating, the detector focal plane array, and then a couple of mirrors. So it's really a very simple instrument. And that's, from an optical design perspective, that's generally a good thing, because it means we're minimizing transition losses. We have high photon throughput, and the spectrometer is designed with to be an f1.8 instrument. So it's a very fast spectrometer. It accepts a lot of photons, which again improves the signal to noise for picking out these subtle mineralogical signatures. Let's see, what else to mention about the instrument that's interesting. It's designed for very high uniformity, which is another important characteristic that we want to have for making these measurements. The uniformity of the spectrum, that is that we're collecting a spectrum with the same wavelength calibration at every crosstalk location, is extremely important for having consistent maps of these mineral features, and for putting the band positions in the right places, as well as for accurate atmospheric correction. Another thing I note about the instrument, it's another way in which it's kind of progressive, is that it utilizes onboard cloud screening. So we'll actually be catching clouds at the instrument so that we don't have to downlink that data, and can actually increase the volume of useful science data by a factor of 2 by recognizing and not downlinking those cloud contaminated scenes. So that's another unique aspect of the EMIT instrument. So this is what it looks like, both outside and within its housing. So a big challenge for any cryogenic instrument like this is rejecting all of the heat. So there is a bunch of active cooling going on, and then a radiator to radiate that heat out into space and keep the instrument, the focal plane array, and the spectrometer cool, so that it operates at a high performance. We've got the electronics base plate that sits underneath, and this holds all of the control electronics and avionics associated with data analysis and handling before we pass it off to the platform. And then, of course, the 2-mirror telescope and the spectrometer, the Dyson spectrometer that you see here in gold. So where are we going? Well, I'll get there in a second, but first, let me show you the areas that we aim to target. Is that a video? No, it's not the video, but you get the idea. We're looking at dust-forming regions, so mostly Northern Africa, Central Asia, parts of Australia and South Africa, Argentina and Chile win, I think, as does most of the Western continental United States. So there are specific regions of the world that tend to be heavy dust-producing regions, and these are the areas that we're targeting. The pink regions that you see around the edges are margins that we've included, so that in case there's uncertainty in the acquisition timing, or of course to get those borderline regions around the dust forming areas to make projections about future climate scenarios. So we're going to the International Space Station. It actually worked out very well that the International Space Station has an orbit which covers all of those regions that we care about in the mid-latitude and tropical zones. And also the International Space Station nicely provides all of the power and network that we require. So it is actually quite an efficient way to work. We'll be on the keel side here on what's called the ELC-1, which you can think of as a big rack that holds custom-made instruments. So we will be launched to the space station and then installed by the robotic arm on ELC-1 to begin operations. And it's a nadir viewing instrument, so there's no motion at all. We just continue looking straight down and turn on whenever we're over a dust forming region. So this is what it will look like over the course of the first 6 months or a year of the mission. Hopefully you can all see that video advance. This represents the different swaths of the ISS that it will paint over the various dust forming regions as the mission progresses. Here, the color corresponds to the solar zenith angle, right? We want the sun high in the sky if possible to maximize the illumination and signal to noise. And that happens in the green swaths. Yellow tends towards our threshold of 45 degrees solar zenith. Of course, we could probably still make measurements at lower solar elevations, and we may attempt that. But nominally speaking, we expect to be able to complete the mission with a 45-degree solar zenith cutoff in the first 6 months of operations, providing an additional 6 months after that of margin to account for cloud cover or anomalies or anything like that could set us back. So we've got good margins on performance and are expected to complete the mission. All right, so let me get into the EMIT data products. I want to leave time for questions at the end. So I mentioned before this first step of going from radiance at the sensor to surface reflectance, and I portrayed that here with the two spectra, the radiance spectrum and the reflectance spectrum. But there are a bunch of steps that come after that as well. There's the production of these mineralogical maps by fitting those mineral features, and then we have to communicate that mineralogical information to the Earth system model. So we'll be doing that by aggregating those mineral maps up to the scale of the Earth that the Earth system models can accept. So this is generally speaking, I think we're working now with a 1/2 degree scale aggregation zone. So we sort of tile the world into 1/2 degree segments and then accumulate the mineral fractions from each segment. So those can serve as inputs, direct inputs into the Earth system models that will then figure out the resultant impact on atmospheric radiative forcing. So you can think of these in NASA parlance as data product levels. So we would call the radiance sensor level 1. The surface reflectance and mineral maps are part of level 2. And then when you go to a geographic grid, it's a level 3 aggregated product. And then finally, these model runs themselves are actually being considered part of the EMIT mission and will be a deliverable to the data archive as well. And those will be a level 4 product. So in figuring out what algorithms we want to use for each of these steps, our requirements were pretty simple. We wanted something that enabled statistically rigorous uncertainty quantification and propagation throughout this whole chain. And EMIT is rather progressive in that respect. I think that we are committed to distributing uncertainties at every product level. We want it, of course, to be accurate, to handle the challenging atmospheres that we will encounter over parts of the Sahara, where you regularly get aerosol loadings up to about 0.4. And we need the algorithms to run fast enough to keep up with the data rates, which are expected to be about 100 gigabytes per day. So I'll talk about the atmospheric correction step first. And this is something that we've had a lot of experience with because every imaging spectrometer investigation generally has to do it. So this is the challenge of taking the radiant spectrum that we observe at the sensor and inferring the surface reflectance spectrum. I'll go into a little bit more technical detail here, just to give you a flavor of the kinds of analyses that are taking place. So for atmospheric correction, although some missions are able to simply take those atmospheric terms from climatology or from other instruments, really with an imaging spectrometer, you can resolve quite small scale features in the atmosphere. So what this means is that we have to we have to estimate those atmospheric constituents from the data itself. Here's an example of a water vapor field with intensity representing the intensity or the concentration of the water vapor over these farms in the Central Valley of California. This is an AVIRIS image that we were testing on, and you can see that, of course, we can resolve all of these very fine scale structures. So really, we need to figure out what the atmospheric composition is using the spectrum itself in order to ensure that we get the accuracy we need. In fact, we're estimating a couple of different constituents. And so here we see transmittance plots. So this is optical transmittance due to 2 different atmospheric constituents. On one hand, we have the water vapor in the cool colors, which represents, so you can see here as we increase the water vapor, we get deeper water vapor absorption features from the atmospheric gas absorptions. Here we have the effect of aerosols as well, which are these broader perturbations. And aerosols are another kind of distortion that we want to estimate, particularly for areas like the Sahara that tend to have high aerosol loadings. And they're commonly expressed as an aerosol optical thickness, plotted here from 0.1, which is a pretty clear sky, up to 0.5, which is quite hazy. So how do we estimate those? Well, so we actually treat it as a Bayesian model inversion problem. This is a common method in atmospheric remote sounding, but it's relatively new in the domain of imaging spectroscopy. So I think it's worth talking about in some detail. So you can imagine a forward model as the model we use, the physics-based model to predict the radiance at the sensor. So we have some atmospheric state and surface state comprised of the surface parameters, which are reflectance in every channel of the instrument, plus maybe a handful of atmospheric parameters, maybe the water vapor and aerosol optical thickness that I showed you before. So imagine that you put all those numbers together in a state vector. We have some radiative transfer model, a forward model that allows us to calculate the measurement at the sensor given that atmospheric state. So this is fairly, I won't call it straightforward, but we know how to do this. We have a lot of experience in doing these calculations. The challenge is estimating the inverse problem. So we have measurement of the radiance in many channels, right? And we're trying to estimate the most probable atmospheric and surface state. And this is challenging because it's underdetermined, obviously. enormously. We have, for n channels in our instrument, we have maybe n+2 parameters we're trying to estimate because we tack on a couple of atmospheric parameters, but we only have n measurements, right? So the question is, how can we do this? How can we constrain the problem numerically in order to make this a tractable inversion? And the answer is we use Bayesian statistics. So you can imagine, for those of you who haven't seen Bayes' rule, this is just straightforward probability theory. If we're trying to calculate the probability of our state vector given our measurement, you can rewrite that as the probability of the measurement given our state vector, and then a prior on our state vector. So the probability of our state vector before we make any measurements. You can think of this as a place to capture all of our background knowledge about what physically plausible reflectance spectra and atmospheric terms look like. And then, of course, there's a denominator here, the probability of the measurement. But if we're trying to invert and find the most probable x, this probability of y term will be the same for all of our solutions. So we could ignore this denominator. So if you do that, and all of their probabilities are multivariate Gaussians, and you take the log of this expression, you get something that looks like this. So this is our cost function that we're trying to optimize. We're trying to minimize the cost. And it has two terms corresponding to these two parts of this product up top. So we have this first term, which you can think of as kind of a spectrum fit error. It's our models matched to the measurements, right? So our forward model based on our state vector minus the y that we actually measured. And you can think of this as a squared error, but it's weighted by the covariance of the instrument noise. So that's this S sub epsilon term. This inverse matrix is the inverse of the instrument noise, essentially. So we want to remove we want to remove the effects of instrument noise on certain channels that are noisy or certain directions of the spectrum if the noise is correlated. And this allows us to do that. The other half of this cost function is our Bayesian prior. So this penalizes departure from our prior S sub A, and it's weighted by the inverse prior covariance. So it also is a multivariate Gaussian. And the great thing about this is this is closed form expression. What's more, the gradient is quite easy to calculate. So you can calculate for any given x that you want to guess, you can calculate your gradient of the cost and improve upon it. So it lends itself quite easily to a gradient descent optimization. So this is what it looks like in practice. We'll take some initial guess at our reflectance spectrum and then use our forward model to predict our radiance at the sensor. And then based on our cost function, we can calculate the gradient of our cost with respect to some change in our state vector. And this allows us to nudge our state vector in the direction of decreasing our cost. So we're making our spectrum slightly more probable, right? Which brings us back to step one. And then we just iterate until we converge. Graphically, well, before I go on, does this generally make sense to everybody? Or is it obscure? I will take silence as understanding. Okay, so graphically, you can think of this as a hill climbing on the probability density of our state vector, right? So here, this graphical portrayal shows surface parameters on one axis and atmospheric terms on the other. And we've got some initial guess, and you can think of the iterative process as moving us up this probability gradient, this local probability gradient, until we achieve some converged state, some local optimum that is a more probable surface and atmospheric state than when we started, right? And when we find our guess here called x hat, we can also calculate a posterior uncertainty using this expression here. So based on the Jacobians K, which are a linearization of the forward model, you can combine your instrument noise and your prior uncertainties to calculate what the posterior uncertainty would be for that linearized model at the solution. So we can also get at least a first order approximation of our posterior uncertainty at the solution. So this is what permits rigorous uncertainty propagation through this process. So here's an example of how this works in practice. This is some work that's being done with some other, one of the co-investigators, Olga Klashnikova, Philip Broderick, who's a member of the EMIT team, and then Michael Garay, who's works with MISR and other atmospheric instruments. Here's a wildfire that was overflown by AVIRIS Classic. And applying this algorithm to every pixel in this scene, right, all of these spectra, we're able to estimate the surface and atmospheric state simultaneously, right? And so this is the reflectance map of the most probable reflectance given the radiance and our prior distributions, right? So you can see we're quite easily able to remove the smoke plume. And then here's the resulting aerosol optical depth of the smoke plume from this wildfire, which exceeds 2 in some cases. So this is really quite a thick smoke plume. To our knowledge, these are some of the highest resolution aerosol optical depth maps yet made, and we're quite happy that we were able to do this despite the terrain being relatively heterogeneous in this area. So this is a good initial validation. Obviously, we're doing more quantitative evaluations based on in situ measurements of aerosol optical thickness also. Okay, so assuming that we're able to get the surface reflectance spectra reliably, the next step is mineral feature fitting. So this is done using a technique that was developed by Roger Clark and EMIT Co-I, which is encoded in the tetraquarter code base, tetraquarter algorithm, but fundamentally it's fairly straightforward. It's a least squares fit of absorption features, removing the continuum. So I don't know if you can see here on your screen, it's a little bit fine, but there's actually a line across the top of each of these absorption features, and this represents the local continuum. So you can imagine this as being the spectrum that we posit would exist if the absorptions were not there, right? So the depth of this hematite absorption feature correlates with the abundance of hematite in the scene. And how you define abundance is actually a really tricky question that we are engaged in, teasing out those finer details now, but you can think of it just intuitively as being the sort of a proportional relation where if you increase the depth of this hematite feature, you're increasing the proportion of hematite that's present within that pixel. And you can use this technique, this spectrum fitting technique, both to identify the most probable mineral or set of minerals for every pixel, but also to evaluate just how much of the stuff is there. And so the best fitting spectrum generally wins. And we do this with a library of a couple hundred spectra that were prepared in advance at the USGS, the USGS Spectral Library version 7. And we're using a subset of that in order to form the mineral spectral libraries that will be used for EMIT. And of course, it will be a continual process of validating and improving these libraries as we start to acquire observations and visit new areas of the world that haven't been imaged before. So here's an example of some of the feature fitting in progress. So just a portrayal this is from Roger Clark's work of the continuum interpolation process here in the blue line over this kaolinite feature and the relative depth of the feature measured between the interpolation point on that continuum and the deepest part of its spectral feature. And here on the right side is a plot showing different potential minerals fitting this used in the library to fit this kaolinite feature. Of course, the only one that fits it very well is the actual kaolinite spectrum, which is just good confirmation that you can use these spectral fit metrics in order to select the right mineral to explain your pixel. Okay, and of course, the next step is to initialize Earth system models. So here it starts to get a little bit more complicated. We're going to back off a little bit on the detail. It's suffice to say there are several processes that the Earth system model assumes. So there's a dust emission module that it takes into account state-of-the-art brittle fragmentation theory to simulate how dust is produced from different regions as a function of wind speed. It's basically dust particles that are already locked into the atmosphere collide with others and sort of knock them off the hard surface and create more dust particles. And of course, that can be modeled quantitatively. So that's the role of the dust emission module. After it gets into the atmosphere, there are Mie scattering modules that will analyze the properties of those dust particles, both their composition provided by the mineralogical maps, but also assumptions about size distributions in order to provide information like the optical properties of these dust particles when they become aggregate volumes in the atmosphere. And then finally, of course, there's the radiative transfer within the Earth system model itself. So this is where we start to analyze the impact of dust both locally over parts of Africa, say, for agriculture or dust storms, but also globally for radiative forcing. And all of this is contained within the Earth system model. And we've got a couple of different Earth system models. We're using the community Earth system model as well as the NASA GISS Earth system model. So we have at least two examples with slightly different codes to calculate this effect. So in addition to getting an estimate of the aggregate radiative forcing effect, we'll also have some crude measure of the variance on that prediction. Okay, so finally, in the last portion of the presentation, I want to give a couple minutes for questions, but I also want to talk briefly about how we'll be validating these products and uncertainties. The duo there is really intentional, both products and uncertainties, because we'll be producing uncertainties at every stage of the EMIT analysis. It's important not just that we validate the prediction, but also that we prove that the uncertainties we're predicting are consistent with the errors that are actually realized in those data products. So there's sort of a second order validation that we desire to complete as well. So the validating the reflectances is fairly straightforward. This has been this is a methodology that's been long established, and you basically use an imaging, or I'm sorry, a field spectrometer like this ASD device that here shown by Scott Nolte of JPL, with a spectral on reference panel. And using a ratio against the radiance, the upwelling radiance from this panel, you can evaluate what the reflectance is of a large stable surface like a playa, for instance. And so you would measure this playa surface, and using that ratio, figure out what its true surface reflectance is. And you compare that directly to the surface reflectance that's estimated from the remote measurement. So here's one such validation that you see here, where the in situ and remote measurements line up, and that gives us good confidence that we're getting a reasonable result. But of course, you also have error bars on this reflectance that I'm not showing here, but it's also important to evaluate the residuals and whether the residuals that you get, that is the residual fitting error, is consistent with the error bars that are predicted to. You can do a similar thing with the mineral detection. So here's an example of a bunch of scenes. We did a little field excursion to Cooperite, Nevada, which is a very mineralogically diverse region of the southwestern US. Here showing a lot of different mineral features in the shortwave infrared and visible ranges, both the remote measurement in red and the library fit in blue. And so what this does is it validates that the mineral that we detected at any given location is actually present at the surface. So we did this at several different field sites that you see here. And this is the sort of validation that we can use also to demonstrate that the mineral detection process of the EMIT analysis is actually is also giving us reasonable results. I mentioned uncertainties, so I do want to emphasize that uncertainties are actually important, not just for the understanding our errors, but also for getting the right answer. This is a simulation that was undergone by Nimrod Karman, recently published in Remote Sensing, looking at how uncertainty predictions in the reflectance can actually be used to improve mineral fitting. The basic lesson is that if you know which channels and what directions are most error prone, then you can downweight those in the spectral fitting metric and actually get a more accurate and noise resilient result. So here, this plot shows the error distributions for the blue approach, which is sort of ordinary least squares. And then in the orange, you see the approach which takes instrument noise into account. So if we're able to produce these reflectance uncertainties, we can actually utilize that in downstream processing to get better, more accurate spectral fits. The lines here show the errors as the noise increases in the spectroscopic measurement. And the fact that the oranges are consistently below the blues simply means that if you take the uncertainties into account, the spectrum fit is actually more accurate, or the prediction of that band depth is more accurate. And so we'll be validating uncertainties using a variety of different tricks, but one of the most common ones that we detailed here was to use scene invariant properties. So you can imagine this stonewall playa area of this mosaic over Cooperite that you see here is pretty homogeneous, right? We've got lots of pixels on this playa, but it's the montmorillonite feature on this playa doesn't actually change so much, right? So you can actually use, to first order, the variability in the montmorillonite retrieval over stonewall playa as an empirical picture of the noise of the mineral detection stage, right? So if we accumulate a bunch of detection pixels here and look at the montmorillonite feature depth, you get a histogram that looks like the red bit here. The predicted uncertainty in our mineral measurements by propagating through the instrument noise is the black Gaussian line behind it. And the moral of the story is that these are actually quite consistent. It's good news that our predicted uncertainties in the mineral feature depth measurement actually envelope the uncertainties that were realized by looking at the variability of our stonewall playa measurements. And of course, you can do the same thing for reflectance, which you see here in the top plot as well. So by using various discovered and known properties of the scene, we can actually get some second order validation on our uncertainties as well. And then finally, we want to have some understanding of how this information will be used by the Earth system models to validate that it will actually make a difference. This is work recently put in for review by Dave Connolly at Cornell using a single column atmospheric model. So in this case, we simulated EMIT observations through the entire retrieval process of making a noisy measurement and then inferring the mineralogy to see how, if we were to propagate that information through a single column Earth system model, that is a simplified version of the Earth system model, how that would, how that would actually influence or improve our understanding of radiative forcing. And here you see on the horizontal axis, the radiative forcing over a desert region for various different posited truth scenarios, right, where we assume different quantities of iron oxide dust in this desert and retrieve it. On the vertical axis, you see what the Earth system model actually predicts based on the EMIT measurements. So the takeaway is that with this improved mineralogical information, we actually expect the Earth system models will do a much better job of predicting radiative forcing, given a pretty good proxy for what the Earth system models are actually doing. Okay, so in summary, the EMIT mission is just one example of many imaging spectroscopy missions that are both planned or recently launched or anticipated for the near future. So much of the same techniques that I was talking about here will be applied on much larger scales in the coming decades, which makes it a really fun and exciting time to be involved with this research. But EMIT itself has the goal of looking at dust producing regions to map their geology and infer the resulting impact on dust radiative forcing. And we'll do that through this chain of products that you see here and validate those, both the first order products and the second order uncertainties through a variety of field experiments once the mission gets underway. All of this, both the code and the data, will be made available to the public. So we're hoping people will find uses for the EMIT data far beyond our own project. We're also making open source all of the code used for atmospheric correction, actually at every product level. So we're open to collaborations or fielding questions on any of this. If you're interested in contacting us about how to use this code or what the data will look like, or if you have independent interest in mineral dust radiative forcing, that's all cool too. So thanks a lot for your time and for listening to the talk, and I'll field any questions. Any questions? Go ahead and just shout them out. I actually can't see if you're the chat currently, so feel free to just unmute and shout.
David, I see one question in the chat. It's when will EMIT start producing data?
Yeah, we're targeting an early 2022 checkout. So we'll hope to be on the ISS early in 2022. And there will be a period of about 3 months, I think, 3 months, if I remember correctly, where we do our on-orbit checkout. And we'll start producing data, delivering data to the archives about 6 months after that for the first radiance and reflectance products. There's a slightly longer delay for some of the higher level products, but it should already be usable, the data, by that time. And then there's the chance that we'll do maybe one major reprocessing of that data based on updated calibrations, et cetera, before the end of the mission.
Thank you. I see some questions about, is this talk being recorded? Yes, it is. David, would you be willing to share the slides with us that we can post?
Sure.
Okay, so we'll post the slides and we'll share it with everyone. And then there's one more question. Are there any optical cleanliness issues with being on ISS? Also, please explain the x-axis on slide 44.
Slide 44. Okay, yeah. So let me answer the first question first. I think my understanding is that the ISS, and I'm really not the best EMIT team member to be asking this question, but my understanding is that while the space station does tend to be a quote unquote dirtier environment in terms of contamination than, say, a free-flying spacecraft, that there's still not expected to be any challenge for EMIT. So we didn't have to change our design much in order to accommodate, say, the contamination from an arriving spacecraft or anything like that. Although we certainly were tracking and analyzing those issues to make sure that they weren't a big deal. And part of that has to do, maybe part of that has to do with where we're located on the station. I'm not totally sure there, but I know that it's not expected to be a major problem. We're almost more concerned about contamination during the construction of the instrument and its storage and installation. A question about the slide 44 axis. Let me jump back there and answer that directly. So there are actually two. I was speaking about this radiative forcing plot. So you can think of this as the truth that we posited in each of these simulated cases versus what was actually estimated by the simulated remote sensing system, right? So you want to be on the 1-1 axis. And we did this for both radiative forcing, the ultimate quantity, but also for the abundance of iron oxides on the surface. So these are just two different stages within the EMIT analysis, showing that at each stage we're more or less getting the answer right, but we do suffer some degradation at the very high aerosol optical depths, right? So this AOD represents the thickness of the atmosphere, the optical thickness of atmospheric aerosols. As the aerosols get thicker, they're more difficult to correct, and you also suffer a loss of opacity in the atmosphere, which makes it more difficult to measure the surface, right? And those two factors combined mean that as the aerosol optical depth increases, we tend to diverge from this 1-1 line. That is, our measurement becomes slightly less accurate, but it's still pretty good and a lot better than what the Earth system models have now. So we'll be using an aerosol optical depth cutoff of about 0.4. So we probably won't be, although we'll acquire the data at higher aerosol optical depths, we probably won't be feeding those into our mineralogical maps, just because we want to be ultra conservative.
Thank you. I have a few more questions. The next one is, are the data going to be available for research purpose?
Absolutely. Yep. Okay. And that's just NASA protocol. It will all be made available. Yep.
Okay. Are you utilizing any radiometric calibration beyond large invariant sites?
Yeah, we've got, well, so we'll do a couple of things. It's a great question. So there are different aspects of radiometric calibration, right? There's the magnitude of the radiometric response, and there's also the relative radiometry of all the different spectral channels and all the different elements on the focal plane array. And we use different strategies to tackle those different aspects of radiometric calibration. To begin with, we'll be starting with a very solid, we hope, laboratory radiometric calibration. So we'll be characterizing this instrument exhaustively in a thermal vacuum chamber, right, to figure out its radiometric response using known sources. So NIST, SI traceable sources. When you get into orbit, of course, you want to confirm that your radiometry hasn't changed and to update it if necessary. So one strategy for that, as the questioner mentioned, is to use these large surfaces. So if we can measure the reflectance of that surface, we can then propagate that measurement to the atmosphere to see what the corresponding radiance would be, and evaluate, whether what we think we measured is actually, correct, right, to within the uncertainty of that measurement and propagation process. So it's not as good as a laboratory calibration, but it's basically all you can do when you get into orbit. There are other aspects of, or other sort of invariant properties that we can use in order to check our relative radiometry. So this is the spectral shape, if you were. So you can look at things like bright clouds that have well-constrained radiometries in the blue to UV range of the spectrum, right? So there are ways we can use those sort of spontaneously or opportunistically discovered objects to see if our radiometry has changed.
Thank you for that. The next question is, are you able to target specific events? Are you able to target specific events or SFC-based sites from the ISS? Events meaning something like the significant Saharan dust outflow event this past June.
Yeah, it's a great question. So our nominal process will be to schedule all of our observations a couple weeks in advance, I believe, although there's discussion about how we might make that more flexible to accommodate events. So I don't think I have the authoritative answer on that just yet. It's something that we'd certainly like to be able to do, because it would be fantastic to actually catch a dust plume. While I say it's not part of our mainline science, right? We're really interested in the surface. It's probably also true that we can provide some information about dust optical properties as well. That's more of a research area, so we're not relying on it for our baseline science objectives. But it would be great bonus science, and we'll definitely go out of our way to try and make that happen. You can imagine other significant events that might be useful, that EMIT might be useful for. Imaging spectroscopy was used for the oil spill in the Gulf, for instance. It was used for looking at the World Trade Center disaster. So there are lots of other scenarios where events might benefit from imaging spectroscopy, but that is not part of our baseline mission currently, and it's not part of our planning.
Thank you, David. In interest of time, I see 1 minute left. There's one more question that I'll take, and then we'll close it. This is going back to if the data will be available. Do you happen to know where the data will be available that users can access?
Yeah, so we'll be delivering all of our data to the Land Processes DAC. So the NASA has a range of digital archive centers called DACs, and they sort of each one takes charge of a different area of NASA's expertise. There's an ocean processes DAC, there's a land processes DAC, and we'll be delivering to the land processes archive. But that will be accessible through a wide range of different NASA discovery and download tools. And a short web search will come up with those interfaces.
Thank you, David. I think that I covered all the questions that were in the chat, at least. I see we're at the top of the hour, so I would like to thank our speaker for the talk today, and thank you everyone for attending. Stay tuned for our next talk, which is going to be on December 9th. It will be on Earth observation, addressing sustainable development goals, and global environmental challenges. We'll be sending out an email about that. Thank you.
Great, thanks everybody.
Hello, Dave.
Yes.
Alex Getz here. Voice from the past.
It's a pleasure to meet you, sir.
I had a question. I guess everybody else is off now, but there is a problem between going from the first AVIRIS to push-broom instruments, but internal scattering in the instruments. Has that been solved? Because there's a lot of scattered light. I don't know, Joe Boardman worked on this problem, and I don't know if anything has come of it.
Yeah, we have been working on that, in fact. So the strategy that we're going to use for EMIT is what we've been using these past couple of years for AVIRIS Next Gen as well. And that is to try and measure and I assume here you're referring to the infield scatter, that is the sort of broadening of the point spread function.
Right, the fact that the scattering is different at different wavelengths, basically, and it somehow has to be accounted for.
Yeah, so we're going to try and measure that scattering function and then do a deconvolution essentially on a frame by frame basis. And we'll definitely have to take into account like order sorting filter boundary effects and things like that. So we don't claim to have the problem licked yet, but we do have a correction that we've been using on AVIRIS Next Gen that sort of pushes us in the right direction. So that, yeah, the idea is to just condition that extended point spread function in order to better approximate the Gaussian. And you can use a linear deconvolution that actually the method we're using now comes from a paper by Zhang et al. In 2009 that basically measures the point spread function, treats it as a linear operator, and then you take the inverse of that and just multiply it through to remove the extra scatter. This relies on having a good measurement of the scatter function. So it's tricky. And this is the first time we'll be doing it with the Dyson spectrometer. So that will be another interesting adventure, I think.
Yeah, well, it's very interesting to hear how things have developed since I've been long out of this business. Things were very different in the 70s when we started this stuff, as you can probably imagine. But I see Rob Green has been all the way through, been there through the whole time. So,
indeed, and he's now director of the MDL, our micro devices laboratory at JPL. So he's leading the charge of creating new gratings and slits. So it's the same fundamentals as much as has changed in the past few years. I mean, it's still the same spectroscopy.
Yeah, but it's nice to see how many people are getting involved in the field or have been involved in the field. I mean, I just look at the number of citations, and they go just from the time I was at JPL, the stuff we created there, and the time, of course, I was been at the University of Colorado for a long time, not anymore, but and starting ASD to build instruments to make all this possible. It's nice to see that it's even propagating out into the medical field.
Yeah, and we've seen it. There's been a huge increase in the food and agriculture domain as well in the past couple of years too. So that's really exploded. And then of course the NASA Decadal Survey, which was the long dream of the history preparatory efforts that finally, I guess, bore fruit with this last round. So it seems like it's really going to happen this time. I'm super excited.
One wonders why it took so long, but anyway. Good. Well, it was a very good talk, and
Thank you.
appreciated hearing about what has gone on in the interim. So keep it up.
Great. It's a pleasure. Thank you.